Adar is the imaging and computer vision team leader at CEVA, and over the last 10 years he's conducted research in the areas of video and image processing and has developed on a variety of DSP platforms. So please welcome Adar.
Good afternoon, my name is Adar Paz. I'm from CEVA DSP. A few words about CEVA. CEVA is an DSP IP company. That means that we license our hardware, DSP core technology, plus development tools. In addition to that, we develop a lot of optimized libraries and applications like stabilizer and super resolution that can be run on our DSP. And if last time in the last convention we talked about imaging and DSP implementation, I thought this time it would be a good idea to talk about computer vision and what is computer vision without feature detection and extraction and matching. So first, let me just say that when I started developing computer vision about 10 years ago, most of the applications were based on Harris corner points and KLT and tracking. And as the computer vision world developed, we saw that there are different types of features that are good for different types of things. So I don't think there is one feature that is best for everything. We have to fit the technology to what we're doing. If you want to do tracking, maybe we want a feature that can be precise in location, that we can find the sub-pixel accuracy of the feature between two images. And if we're doing object recognition, maybe that's not as important. But we want to recognize the feature within images in different quality, blurred images, rotated images, and maybe even images that have passed through different sensors, like in medical application, that you want maybe to match a feature in an MRI image with an X-ray image. So I'm going to try to convince you in this presentation that DSP software implementation is the way to go in the world of computer vision. And I'm going to try to do that by saying that we have all these applications that use feature extraction and description technologies. Stuff like gesture control, augmented reality, depth map, driver fatigue. And we see that these applications and more are helping different kinds of markets, like mobile, wearable devices, that's pretty new, surveillance, and I think the very exciting automotive market, which has, I think, is defining the computer vision application needs. And we see, when talking to these clients, that all these applications that sometimes you can see, for instance, gesture control is good for mobile device and also for automotive, that everyone is doing something else. Everyone has its own requirements. Sometimes in automotive you need to be set at very, very high standards, while in mobile devices you have more leisure with the application. The performance is different. But this thing is blowing out of proportion. A lot of applications, a lot of use, a lot of cycles, a lot of power. So before we talk about implementing different kind of features on a DSP, let's talk about the alternatives. One alternative for a DSP is to use a hardware solution. So if this is the development timeline, a hardware solution implies that we have to complete algorithm development before we start the RTL design, production, and distribution. This puts a very hard constraint on the timeline of the developing product. If we go on a software, we can start the RTL design. If you base it on a DSP, you can start the RTL design production and go to distribution without even completing the algorithm. You can design your algorithm well through the distribution stage, and even after the product is already in the hand of the user, you can continue improving, even writing totally new applications that you did not even think about when you started this project, because you're on a programmable option. The other alternative to a DSP is a GPU. A GPU is located in many devices, mobile devices, PC, laptops, and might even go into other products such as automotive. And what we found here was very surprising. Let me just explain to you this graph. So we chose several, I would say, computer vision basic kernels, such as Sobel, correlation. Correlation separate what it means that we want to do a correlation of a 5 by 5 matrix, but this 5 by 5 matrix is a separable one. That means we can separate it to two 5 by 1, 1 by 5 vectors and do a two-pass approach, which is more cycle efficient. We have a histogram, which is, I would say, data load store intensive, point operations such as color conversions, min, max, median, corner Harris, which is multiplication intensive, and average. And what you see, the y-axis here, is the performance factor of by how much the DSP is more efficient than the GPU. For instance, we take the first one, that's the Sobel. You can see that the DSP performs 10 times, it gives 10 times the results at the same timeline than the GPU. You can see that in GPU B, it's 20 times better or performs faster than the GPU. So on average, we see an improvement factor of an average of 13. And if we also take into effect the fact that the GPU cycle and GPU is about 5 times more power expensive than the DSP, than the CEVA MM3101, then it's about 50 times more efficient than a GPU. So I hope this convinces you that the DSP option is the more efficient one in the sense of cycles and power. Typical feature flow, before going into, we're going to dive into several features. I divided the process into 4 stages. I would say first, we might have to do some pre-process to the whole image, and these are filters that are done very well on a DSP and on hardware. Sobel derivative is an input for Harris, and I would say Gaussian and image pyramid are allowing us to be scale invariant when wanting to do feature detection, integral sum for surf. And on top of the processed image, we can detect key points. Key points are special points in the image that we would like to track on or find in other images. And for these points, we have all these different methods to describe the point or give a classifier for these points. And in the end of the day, in order to match a point in one image to point in another image, or a key point in one image to a key point in another image, I would have to run some matching algorithm, decision tree or SVM method to match the classifiers. So we're going to talk about fast, surf, hog and brief, and how the DSP is good to implement these guys. And I decided to start with hog, which I think is a very cool concept. It's a little different than all the other concepts. Up to seeing what the guys with hog did, I was thinking that in order to do object recognition, that the object is sum of its features. Classic object detection would detect features in a reference image and then try to find these features in a target image. And if I found enough of these features, I would say, okay, I can see this object. But this does not work well with pedestrians. When I walk, I I change the form. I'm not a rigid object. And feature detection, feature description pretty much wants me to say, to stay the same, to stay rigid. And these guys found the concept to somewhat softly describe an object and then find it in a target image. And generally, this is done with the following modules. First thing we do is we scale the image using a bilinear scaling. That's in order to be scale invariant, to find people of different sizes. Next thing to be done is gamma normalization. We want the classifier to be able to work on images that were taking in different light conditions. Gradient calculation, and that's the main point of the HOG, that's histogram of gradients, and descriptor calculation, which is the histogram of the gradients. And I know that people after me are going to talk about HOG, so I'm going to let them explain. I'm going to get into the details. So the first thing I said we need to do is bilinear scaling. And if we choose to do bilinear scaling in an efficient way, we would like to do it with 3 multiplication. I remind that we want to interpolate some place that's not on one of the 4 pixels. And we're going to use our 4 neighbors to do a weighted average. And the weight is a function of the distance from the pixels. So in step 1, I will do vertical interpolation. In step 2, I want to do horizontal interpolation. This is challenging for a SIMD DSP architecture, because usually what SIMD likes to do is load 2 vectors of linear data and then do some kvetch, some computation. So step 1 is very efficient for regular vector processor, but step 2 is not so much, because how do you do intra-vector calculation? And I want to do it in a SIMD fashion. I want to do it on many data at the same time. So what the MM3101 has to solve this problem, they say, okay, you load, like I said, you load 2 lines and you do the first step of the interpolation, and then you store the result in a transposed fashion back to memory. And then the second step is just done the same. I can just load again 2 by 8 vector of pixels, do the second step, and output the result. The second block in HOG is gamma normalization. In generally, computer vision has many nonlinear functions. Just HOG itself has the gamma normalization to normalize the input image. It has division and arctangents to calculate the direction of the gradient. And if we could implement these nonlinear functions through a lookup table, we still have the problem of how do I use it in a SIMD fashion? How can I load 8 or 16 results from single lookup table without having a collision in the memory? So this is exactly what the MM3101 technology allows. We can load several numbers from the same lookup table in one cycle into a vector, and then keep on working in a SIMD fashion. We call this lookup table parallel access. So this concept, a very, very powerful concept, will return in the next slide. Let me move on to a different feature extraction called ORB. ORB is an algorithm that includes feature extraction and feature detection. I think it's one of the coolest ideas that came after SIFT. When they said, okay, let's see how we can get features that are good enough to track and descriptors that can be done very fast in a very powerful manner in a low energy idea. So it has the following blocks. Pyramid, as we said before, is for scale invariant. Fast9 is byte corner detection, as opposed to Harris, which is a lot of multiplication and gradients heavy. So this is a lightweight corner detection. We still have the Harris to improve on the Fast9, but this works only after the Fast9 filters 90% of the points of the image. non-max suppress to improve the quality of the detection points. And for descriptor uses the oriented brief, which is also a cool concept that gives you a very small, short descriptor that's easy to compare in the matching in the next stage. So we're going to discuss this one a bit. This is a description of Fast9. The idea is very simple. Instead of calculating gradients, this is what is done. We take the center pixel and we look at 16 pixels on a circle from the center pixel, and we try to find an arc of 9 continuous pixels that are either much lighter or much darker than the center pixel. So within 16 comparison, we would know if this is a corner or not. And the challenge here usually is data access again, because if this is placed in the memory and I try to load in a SIMD fashion these 16 numbers, I would definitely get a collision in memory. So here the solution is an architecture idea with a software idea. The idea is that maybe we can find a quick way to filter most of the points that we're going to know that they're not going to be good for Fast9 corner detection, and then be left with only about 10% of the pixels in the image and do something in a multi-scalar fashion. And I will explain this in the next slide. So here, this is a graphic explanation of what I just said. These are 9 pixels arc. And the first thing we want to do is a quick early exit that allows us to load the pixels in a long linear fashion. So I'm going to say that if the top pixel and the bottom pixels are not much lighter or much darker than the center pixel, then this point cannot be a corner. In order to filter out 90% of the image, I need to check only two points. And I can do that in a SIMD fashion. I can load a long vector of tops, a long vector of center points, and a long vector of bottom points, and very quickly filter out most of the points. Using a technology called conditional flow, I can store only the interest points that are needed for the second pass into a candidate list. And the second pass can do what's called multiscalar. We have only these points left for Fast9 computation, and I can use the SIMD vector where each element in the vector goes to a different feature. And this way I can work on several features at a time. So this utilizes both the SIMD efficiency and random access to memory, which is another powerful thing of the DSP core. The brief descriptor. The brief descriptor tries to describe the patch using 256 pairs of bytes in known places and creates a 256-bit word that each bit signifies if one byte of the pair is bigger than larger than the second byte. And the challenge with the brief descriptor is that the orientation of the patch. In order to be orientation invariant or rotation invariant, we need to do one of two things. One option is to take the patch and rotate it using bilinear bicubic interpolation, and then run the brief descriptor and test it against the bank of the descriptor. Another option is that if I know the orientation, I can call upon the pixel pairs in a rotated fashion. That means if I know the rotation, I can just play with the addresses in the memory. So So the solution with the DSP is to calculate the orientation and then go to a lookup table to find which addresses, at which addresses the bytes are located. I go with these addresses, and in random access fashion, I load these bytes to the vector and go back to SIMD efficiency. Going to surf. Surf is an algorithm that includes descriptors, that includes the whole scheme from image processing, detection, description, and matching. And I think it was inspired by the CEVA descriptor, but wanted to do it much faster, much more efficiently. The strong part of the surf that it's based upon integral sum. And this integral sum allows us to do two special things. One is that it reduces the need or eliminates the need for scaling in order to be scale invariant, because I can work on the integral sum image with all the scales. And the second thing it does, that it changes the arithmetic from multiplication to add sub. And this is very, hardware guys here can tell you that this is very efficient in the sense of energy, power. And we have some tricks in order to optimize the surf. First thing is the integral sum image. So again, like in the bilinear, we can take advantage of the transpose technology, and we can load two vectors, two columns into two vectors, and do the first sum of the integral sum, and then store this in a transpose fashion, and then go upon doing the second pass of the orthogonal integral sum, and this way we can get the results, and the SIMD is working in full efficiency. The second module I want to talk about in surf is the box filter. Actually, the feature in surf is based on these kind of features, where I want to calculate the large box and subtract the black box. And this is the computation that I need to do. This has something like 7 add sub instructions and 1 multiplication. And we have this done on the MM3101 in 1 cycle for several results. So this uses the very powerful filter instruction. And the surf descriptor, which is very, I would say, cycle intensive, based on HAR feature. And for each key point that is chosen, there has to be thousands of calculations of this HAR feature, which is something very similar to the box filter in the response layer. And the challenge here is that again, we need to calculate these things in different areas of the image. So again, we take advantage of the multiscalar or parallel load technology in order to calculate several features in several areas at a time. So we're coming to a summary. We were talking about two-dimensional access in the bilinear and the integral sum. We were talking about lookup table support for nonlinear functions, parallel memory access to work on several areas of the image in a multiscalar fashion, dedicated instruction like the one in surf for the box filter, and the vectorized conditional flow like the trick we saw how to do Fast9 in a very efficient way. And that's the conclusion. A computer vision processor should have large enough internal memory to support the tables, to support the multiscalar, wide memory bandwidth, because we see that some of these features are byte arithmetic. That means we need to feed its very fast processing. We need the load store unit to be able to feed this processing machine. Efficient filtering process, especially for the pre-processing, fast and flexible random access to memory, good bit and byte data manipulation. And these are some of the work that has been done in feature detection, references for you guys. And you're all invited to see the orb demo that's shown in the showroom. And that will be all. Thank you.